Okay, so let's summarize then the idea of EMF for the whole chapter then. The force on any charge is equal to QE plus QV cross B. So there's a force due to the electric field and a force due to the magnetic field. So the force per unit charge is E plus V cross B. This is always the case. Now, the definition of the EMF, if you go around a closed loop of wire, the definition of the EMF, it's the integration of the force per unit charge dotted into the elements of area as you go around. And we've discussed this before. This is the fundamental definition of the EMF for a loop of wire of any shape. And it can be shown that this EMF is numerically equal to the work per unit charge going around the loop. Now, the magnetic field, the magnetic flux could change due to two reasons. For instance, let's take this example. You have a rod that's moving with a certain velocity and it's moving on two rails, and you complete the circuit with a meter that has some resistance also. In the rods have some resistance. So the important point here is that as this rod moves to the right and there's a magnetic field, the magnetic flux could change due to two reasons. The magnetic flux is changing because the rod is moving, so the wire is moving, so the area is changing. But also, if the magnetic field itself is changing with time, also that could lead to a change in magnetic flux. So in general, the rate of change of magnetic flux could have two reasons that it can change. And when you take the derivative of the product of two things, you get the first times the derivative of the second plus the second times the derivative of the first. So you could get a change in magnetic flux because the magnetic field itself is changing with time, or you could get a rate of change of magnetic flux because the area is changing with time, or both things could be happening at the same time. So in general, the magnetic flux can change due to two reasons. And you can prove, and we're not going to go through this proof in this course, but I do have extra more advanced notes if somebody wants to look at this in more detail and understand it better. You can prove that the EMF defined this way, you can prove that it's equal to the negative rate of change of magnetic flux for any case, no matter what is happening in the problem, no matter if the magnetic field is changing only with time and the wires are fixed, or if the wires are moving and the magnetic field is constant in time, or if both things are happening at the same time, the wires are moving and the magnetic field is changing with time. It doesn't matter what the reason is, you can prove once and for all that for any case, the EMF is always equal to the negative of the rate of change of magnetic flux. And that's the thing that makes this chapter very easy, because you only have one equation to get the EMF. For instance, if you take the rod as moving, as I mentioned, the rod that's moving to the right, and the magnetic field is into the page and it's changing with time, it's increasing with time. So you could get induced currents due to these two effects. You could get an induced current due to the rod moving, and you can get an induced current due to the magnetic field changing with time. But the nice thing is that always, no matter what's happening, the EMF is still equal to minus d phi by dt.